So I'll be an odd man out in the sense that I'm really not talking about deep learning, but really more about both reinforcement learning, but about methods which were highly unpopular in reinforcement learning when we started using them, and so for some bizarre reason in deep reinforcement learning, a lot of people are starting exactly at the trajectory where we in robot reinforcement learning took off 15 years ago, and maybe I can help fast forward that development by bringing, what we have learned a little bit to you. The second part I want to bring to you is our problems which we have in robotics, since I think it would be really, really good if more people would actually be focusing at bringing really these, really focusing deep learning methods on such kind of problems. So let me start with a video. And in fact, this video is from the time when robotics was considered as cool as deep learning is considered now. That means it was in the 1960s when the first industrial robot was ever built. And they were so cocky that the first advertisement they created immediately an advertisement on the first industrial robot and said, "You'll have a home robot within no time." So this is a really commercial from 1969. And the first industrial robots were built in around 1965 by George DeWolf. And you directly see this is what we would love to have in a robot at home, right? The amazing part is, our robots actually, they look different, but they're controlled in exactly the same way as they were back then. And just like back then, you could, by now, create an army of graduate students, and with an army of graduate students, you can automate any kitchen. Problem is just, you would automate one particular kitchen, not actually the generalized kitchen, which works for, arbitrary, excuse me, this one goes into my ear, it's really, how can you guys deal with that? Directly goes into the ear. So luckily, the anachronism of the social situation of back then has big time changed. The robots look much prettier, but actually the intelligence in most robots you have around the world is about as bad as this one. And nothing in here is, fake, except for the opening of the bottle. I'm pretty sure that one was completely faked. Everything else you could program, and the biggest difference today would be you need probably fewer students, and the robots are substantially cheaper if you wanted to stage this kitchen demo. So what have we done wrong in robotics? Well, I think one of the biggest thing we did wrong is we blindly automated a task. And this works very well for the car industry, where we want to produce 10,000 cars of the same type, and every single part is sufficiently expensive that it's worth to put an army of engineers on them and to then, make this all work. Now, I think I should, probably not, it's nearly over. I'll not fast forward through this. But on the one hand, we could do it tomorrow. On the other hand, that would be the most expensive kitchen to have.
These Brits have champagne breakfast all the time.
Come again? So, big question, I think I answered it already partially. Why don't we have such robots? Well, we blindly automated. We gave them basically no intelligence. This works for factories. It really doesn't work for any environment which is open-end, open world, where lots of things can happen. So what we really need is learning approaches in robotics. And I want to quickly take you onto a small journey in what actually makes robot learning problems special and different from the learning problems people encounter when they work, like, I don't know, on some OpenAI benchmark tasks where you can do a trillion of trials and then you hopefully have a good-looking policy. And with that, let me start. Well, first of all, we have a pretty high-dimensional task. What you have here is a task where you're paddling a ball on a string, and it has an internal state, where the internal state is the state of the arm, velocities, is in positions, and an external state, which is again the state of the ball, which is again would be velocities and positions. And that's already like 14, 15 continuous dimensions, and you have to actually actuate it at the arm level which gives you pretty high-dimensional output dimensions. This made it really, really hard to use classical reinforcement learning methods from off the shelf, because they relied on Q functions, on modeling really the rewards to come after for every state after every action. And in order to get such a Q function, you have to really fill up a very high-dimensional space with data. And even worse, you have to search in this Q function, which already means finding a single good action can be as expensive as basically computing a complete policy. So what we in robotics realized relatively early is that you need to go for parameterized representation of the policies, which in reinforcement learning at the time when we in robotics started this was something which was more or less of a no-do, since it seemed to be so much easier to just derive a good policy from a Q function. So first lesson basically was, well, we need to find parameterized policies. Good, that's already, well, deep learning is all about parameterized systems, and when you apply them to robotics, that obviously would be about parameterized policies. So that makes sense. Now the second problem is, well, we basically are living in a world where we are on the one hand interacting with the physics, and well, ignoring physics really hurts. Since when you do a bad action, that can really destroy your robot. And every action can really badly destroy your robot. In classical robotics, people actually said, for that reason, you should just trust the physics model. Make it as good as you can and trust it. But it turns out that whenever you're running an optimizer on a physics model, and you're not doing a lot of hacking afterwards to fit your optimal trajectory, optimal policy to your robot, well, in that case, you are most likely breaking your robot. For the simple reason that a small physics error is directly recognized by the optimizer, and the optimizer will see, oh, here is something how I can win, win and create a policy which is maybe not very physical, but which actually makes a lot of sense. So if I, for example, had it that I optimized the policy and there was, that there was a small error which meant, due to the negative inertia which you have on real built robots, but it's due to internal state, and which resulted in something which was like negative friction, which obviously made the optimizer think it had a nuclear power station built into the robot, and it could draw any energy out of it. And the first thing the optimal policy did, which looked perfect on the physics model and in simulation, was on the real robot, this, and it broke the arm, and it made me, it created me a 10,000 euro bill. So it's very, very easy to use a model in the wrong way, even if it has just a 5% error or 2% error. If you optimize on it in a robotics task, it can completely destroy you. So what we really, really need to do, and is that we need to trust our training data and not the model as much. Just use the forward model at best as a guiding tool in order to steer the policy learning process. And this is again something which I think is, well, this is really, really quite important and quite different from the mainstream way of how reinforcement learning used to think about these things. Now, but we're obviously interested in many states, many actions, so we're really interested in paths. And in most cases, it makes sense to write down robotics tasks not in the state action space, but not so much as in the trajectory space, since in the end, the trajectories have a lot of regularities which give us a nicer way of formulating things. And unfortunately, we have very, very few trajectories. We can write down reinforcement learning problems quite nicely in robotics when we write them down in terms of trajectories. We nearly never have stationary distributions, which are commonly assumed in reinforcement learning, because usually a stationary distribution means you have arrived at the goal in robotics. And the goal is usually easy to attain. A linear controller can do it. An engineer from the 1950s can do it. While the complete rollout is really much more important. And sadly, of course, the complete rollout includes many small steps in real time at rates of 500 to 1,000 hertz, where rapid or aggressive exploration is deadly for the robot. So with other words, we need a lot of temporarily local exploration, which works by perturbing the actions, which requires that we have more or less stochastic policies. And surprisingly, this is what you guys know as policy gradients, for example, has been really one of the key approaches how people work in deep reinforcement learning. The other one is to use massively use models, I think, in order to get good value functions. So you really need here local action perturbation. All over, this brings us to a structure where we have to deal with, on the one hand, trajectories, where we need real-time policies, and then on the other hand, have to, well, a supervisory policy which has to deal with a bit different tasks. We quite clearly need local exploration, temporarily non-aggressive ones, and only very, very few global perturbations because they would really be destructive to the system. And very unfortunately, we have generically little data because minutes of episodes are, well, usually hours of grad student time, and the robot breaks between the experiments. And even when you have built the exactly same robot in 2 different labs, they won't work the same. So I hope this brought you into my shoes. And now I'm going to take you into the journey of, well, which we took through reinforcement learning, and which I think deep reinforcement learning is to some extent repeating. And we really started by saying is that you need to initialize smartly, because we're living in a space where in a time frame where we cannot run so many experiments that we could start from square one, but really have to start from an imitation. Just like just like a tennis teacher usually also takes a student by the hand, shows the student, this is a forehand, and now try to repeat it, and then you take 300 trials before you bring the ball over the net for the first time. Yes?
And so how far can you get with the simulations? You said you need the real robot.
It pretty badly. Actually, learning on one robot and transferring to the other one is still a hard task. Transferring from a simulation, if you have a task which is easy, meaning a task where you don't make contact with the environment and where you're not going for very high acceleration movements. In those cases, these tasks are purely kinematic. You can eliminate the robot, you can make it so stiff that it's like a simulator. In the moment where you make the task dynamic, you make much contact with the environment, basically the simulation is out of the window. So people, for example, have massively done simulations of grasping, and nearly none of these results ever transferred. And well, I'll show you one thing where the optimal control and simulation failed completely, but imitation learning did it out of the box in a second. So key thing, smart initialization, and then subsequent reinforcement learning, where really the key part is that it needs to be reinforcement learning that optimizes the expected return while staying close to the training data. So for imitation learning, I show you here now one example which we weren't capable of bringing. Initially, we had this in a simulator. We used a classical approach. The classical approach never really transferred from the simulator. And then we finally went for imitation learning. We thought this would be a really, really hard task where we would need imitation learning, lots of reinforcement learning. It turned out imitation learning could solve it out of the box. And well, here you see this ball bouncing with a ball on a string, which I used as an introductory example. So in other words, many tasks, if they have a well-defined trajectory distributions, actually can be learned quite efficiently when you're minimizing just simply the distance to the distribution of the task which you have observed. But obviously, as we all know, if you could learn everything by imitation learning, we all could graduate with a PhD from primary school, and it would be very easy, and there wouldn't be all of these exercises and stuff which we have to do in order to get even into the PhD program. So we really do need the optimization of the expected return, and that turned out to be a much longer story. When we started with this, we actually started with the vanilla policy gradient methods, and where the key part of staying close to the training data could be accomplished by simply saying we want to stay close to our last policy. And the normalized policy gradient would obviously be obtained from this kind of an optimization problem where you're just, well, which just represents normalization. And it seems to be like totally, well, it seems to be totally initially the right thing to do, since it's a parametric, it's a gradient, so it gives us good direction, it does small changes. In order to get the policy gradient, you only have to perturb your actions a little bit. So it seemed to be something really, really smart to do. And so we were wondering, well, does it really solve everything? Why wasn't everybody doing that in reinforcement learning? And then we tried it, and it really turned out to be quite hard. And you can even make this particularly nicely clear when you take a binomial policy. So binomial distribution is a policy, and you have a two-state, two-action problem where you receive a reward of 1 here, a reward of 2 here. And basically all you want to do is, if you're in state 1, you want to go to state 2, and if you're in state 2, you want to stay in state 2. So it's a really, really simple control problem, but the simplest possible you could come up with. And then we plotted the policy gradients, and we realized that the policy gradients would always go into pretty stupid directions. In fact, unless you were started right here, you basically had no chance of ever getting anywhere close to the optimal solution. You would always converge to the wrong solution. So what's actually the problem here? Well, the problem is that policy gradients in reinforcement learning violate the Kiefer-Wolfowitz conditions pretty much anywhere where the policy in the end has no exploration. And exploration is expensive, so a policy gradient will always try to first do away with the exploration, and then it unfortunately has converged at a solution where exploration, well, no longer happens. With the result that we were pretty frustrated, and then, well, obviously conjugate gradients or Hessians or anything didn't really help. And then, luckily, well, we stumbled upon natural policy gradients. We stumbled upon natural policy gradients, which basically, as most of you know, well, they don't take the regular unit metric, but they just squeeze it a little bit. Oh, I'm sorry, you can't see what's on the. So this is the identity metric. This is the fish information metric, and well, the gradient obviously is different. If you're doing a line search, you get a different error. So if you bring in, if you bring the natural gradient into policy gradients, you really get very different gradients. When you look at this problem here, so again, this control problem, you see that all gradients now lead you to the optimal solution, and they never want to go for zero exploration. So it really makes a huge difference, and there's an equally nice problem, the simplest control problem ever, the LQR problem, where you can show that, all gradients lead to zero exploration right away, and there the natural gradients even all point directly to the optimal solution. So you could go with a single step to the optimal solution if you like to. So that seemed pretty nice. But, in fact, we could even prove that the natural policy gradient is a true policy gradient, and that we could, well, find we could find really fast estimators for it. And interestingly, things like TRPO, so many of the state-of-the-art reinforcement learning methods are just variations of this theme, where they, well, employed the same insights from what we had 15 years earlier. Now, in robotics, this was pretty much how far we got the natural policy gradient. Yeah. Now, you don't see here trial by trial. This is actually every 30th trial or something, and this was a really, really good trial run. The normal trial run for doing this T-ball-like game was around 800 to 1,500 times you had to hit the ball on this T-stick until you actually got it to have a really good speed. That shows you again how hard it is to be a grad student in robotics, since you are the one who are picking up the ball all the time and put it back onto the stick. And it gets a reward based on how far it actually shoots the ball, and it gets a punishment on the joint level speed of the robot, so that it doesn't go for the very, very high speed, just hitting somewhere, so that it flies somewhere and breaks the robot. So way too slow, and again, we hadn't solved everything. Now, this brought us to finding now a long forgotten reinforcement learning paper where people had realized that you can treat a reward like an improper probability distribution. And which basically is something very, very simple when you look at it from a bandit point of view, that if you have taken lots of good actions and some bad actions in many different states, well, you want to reproduce the good actions, but if in some states you only have bad actions, you rather want to reproduce these than take something crazy and completely new. And it turned out that this is nothing than imitating yourself in reweighting the samples which you have taken by the reward, treating the reward as an improper probability distribution, which obviously leads to an EM-like algorithm, and in some cases can be completely boiled down onto supervised learning, like reward-weighted regression. Again, we were really happy, and since we thought now we finally have solved reinforcement learning for robotics. Turned out that, well, it works relatively well. What you see here is an example of it. Again, we start this time with an imitation of this ball in a cup task, or kendama, I think, as it's called in Japanese. And the robot fails because it can't produce the accelerations which the human has, and instead it doesn't have any hand-eye coordination out of the box, and it simply has to self-improve. And usually after 40-something trials, it gets the ball into the cup for the first time. And after about 90 trials, it actually becomes perfect. So I don't think any human becomes perfect. In fact, the humans we have actually studied did usually maxed out around 60 or 70%. So in that sense, our robot was definitely better. In terms of learning speed, it turned out that kids at the age of 6 to 8 managed to not learn it at all. Well, at least in the ones we tried. The 10 to 12-year-olds managed to learn within 30 trials, so they are to get a ball into the cup for the first time, which is slightly better than that algorithm. And grown-ups usually take 3 or 4 trials, so it seems to be only me who took 3 months to learn it. And we used, of course, chocolate as rewards for the kids, which is much better than numbers for the robot. So again, we thought all solved, and it actually turned out that this idea in EM algorithms that you're fitting a lower bound, of course, means that you're taking a convex function, you're sometimes fitting it to a plateau, and that means you're doing many, 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 many small steps. And sadly, in most problems we have a lot of plateaus, so we came up with more and more complex policies which had to add more and more stochasticity just in order so that we would avoid the plateaus, which felt pretty sad again, and we, well, again, needed to move on. And then we finally stumbled, I think, on the way where we are really now sticking, and we call this relative entropy policy search. It actually goes back to the original reward function to optimize, that we basically want to maximize the expected return. We now put additional constraints in there. Well, some obvious ones because we treat it all variationally. But most importantly, we have the constraint now that we want to limit the amount of loss of information which you do when you're doing update step. And you directly recognize this was also the key part of the natural gradient. Just this time we can solve for things from a variational point of view and really solve the optimal control problem with explicitly keeping the distributions around. And we get analytic solutions to this actual problem. And that's actually where we are heading, and I'll now switch. I'll tell you a little bit of where things are going on, which was the original title of my talk, the f-Divergence part. Just my student who promised me the slides, and I got them too late to really prove them, to really integrate them the way I would like to. So I've taken you first from policy gradients to natural policy gradients, then to our story into reward-weighted regression EM-like methods, and now really into relative entropy policy search. About these two methods I'll talk a little bit more later, but let me quickly finish that journey. And what we currently really focus on are the f-Divergence policy optimization methods. And this was actually kind of lucky. A couple of years back, I was at a summer school teaching there, and I saw a lecture of Amari Sensei, who said something about the f-Divergence, and I felt we had to look into that. And it turns out that, well, we can replace the KL divergence of the natural gradient by the f-Divergence, which generalizes this whole idea. And this brought us to a whole family, or whole generalization of reinforcement learning methods, which we found pretty amazing. Because when you write down the reps primal problem, so the problem of optimizing the expected reward, subject to the constraint just already written in with the Lagrange multiplier, you would normally have the KL divergence here, and you could then write some feature expectations if you wanted to have either for your trajectory representation or for your value function representation. And when you put in the f-Divergence here, you actually get a pretty nice dual to the optimal control problem, where nearly everything works analogously to before what we did with the KL, just this time with the f-Divergence. And the f-Divergence gives you, well, different other metrics which you can plug in between probability distributions, this than before. So with the alpha equals 1, and the alpha equals 1 actually still has a particularly important meaning for us, but it also gives symmetrically around the Hellinger distance as the reverse KL or the Pearson's or the Neyman and distributions. What we actually figured out is that each of them gives you the one thing which we had not understood when we were thinking about the EM-like methods. Since it actually this alpha gave us a way of how we could derive different types of stochasticity. So for example, if you would take a large alpha like we have taken here, this actually eliminates only very few actions. It usually eliminates, as you see here, the worst action, then the second worst action, third worst action, and third and fourth and fifth worst action, and finally you're stuck with only the actions which are halfway good in this banded problem. Quite to the contrary, if you take a large negative alpha, you will directly focus on the best action and make all of the other actions similarly worse. So this actually recovers two of the strategies which are heuristically found all over the reinforcement learning literature. The alpha equals 1 is what the policy which our relative entropy policy research would give. And in the banded case, this is actually relatively similar to the XP3 strategies of, for example, Peter Auer. And then you could find other cases like alpha equals 2, which are also fairly efficient, but which we had not found at all in the reinforcement learning literature. In fact, alpha equals 1 of the KL seems in reinforcement learning to have a very special meaning. Since alpha if it's smaller than 1, it usually means you're trying to kill more aggressively bad actions out of your policy. And you will be, and for certain alphas, you will get then the greedy policy, the epsilon greedy policy, the epsilon soft policy, the alpha equals 1 is the softmax. And then you find things like for alpha equals 2, the linear policy, or the epsilon elimination policies, which nobody has so far, to our knowledge, used in reinforcement learning. And for the smaller alphas, like for the linear policy or the epsilon elimination, you will basically, you will basically kill bad options more frequently. For the bigger alphas, you will be more optimistic, and you will make sure that your winner takes most of it, but the losers get only something. You see, when you look at these plots, these are relatively simple toy problems from classical reinforcement learning. You will see that it is not very good to go extreme, but that it's actually very hard to say where in the middle are the best kind of policies. It's just probably not very smart to be greedy, but it's also not very smart to be anti-greedy, so to only eliminate the worst actions. And what we figured out, I'm missing here one plot, what we figured out is that being somewhere between, for an alpha between 0 and 2, is usually the best range for policy optimization. What is particularly fascinating is when you then bring this to complete reinforcement learning, so with the state and action complete, and they're not just the bandit problem. What we actually see is that actor-critic reinforcement learning falls completely out of it as well. And this actor-critic reinforcement learning has, on the one hand, the REP solution, where we have the softmax policy update, which you see here, but a type of critic, which is a log-sum X critic, which people were normally not using. While if you use the Pearson inequality, Pearson divergence, you actually get a critic which has a squared Bellman error in here. So it corresponds exactly to the critic which people have used so many times in reinforcement learning. But the policy update is now a linear update where you're reweighting your policy by just a linear update factor every single time, which is somewhat slower. And these two steps are compatible, so they will actually work in sync relatively well and converge to an optimal solution. And you can put in gradients for both of these and explain a lot of algorithms from the literature while actually telling why some of the heuristically developed reinforcement learning methods do not generally work. Coming back to robotics, we obviously use the reinforcement learning methods I've been telling you about in a bigger scheme where we want to learn many policies, and I'll show you a few more examples. Where we first create a database of policies, like here for a table tennis task, we parse them into a database of forehands and backhands, and extract them from the stream of data, and then particularly want to learn the fast stochastic policies, and then which do local exploration only, while a gating network switches between these on a slower time scale and gives you global exploration. Here we have massively been using relatively entropy policy search, and initially we only simply plugged in the option, the type of which policy we were using, and already by putting this in, we could, within relatively little training time, so that here is after 3 hours of training, we have actually had faster algorithms which can now be trained by within about 20 minutes. It's to achieve even better performance. You can actually train your robot to play table tennis against you. However, this turned out to be naive too, because just inserting now 2 layers into one for selecting the kind of action, the kind of lower level policy you're doing, and one for selecting the actions given the lower level policy, really hurts you in the moment where you have choices. So here you see a choice of fitting it to the left and to the right. Anything in between won't really work. So it's no longer, it's really decision choice, and you can't do something convex in between. In this case, this naive insertion of the option will actually make us, a system generalize over the 2 different possibilities which were good, and never really have the options focus on one of them. If you limit the amount of responsibility through basically putting an entropy constraint on the option selection given state and action, well, in that case, the behavior specializes and they jump onto the optimal solution and really reduces the number of primitives. This gives us something which we called hierarchical entropy policy search, where we still have to put in the f-Divergence yet, but it allows us to have an even better performance, and also to effectively reduce the number of used policies, sub-policies in there, in order to get better performance. Key. Then I'm at the outlook and the conclusion. Well, we're really at the core of machine learning for robotics, but this obviously relates to other fields like robot engineering, way more machine learning, and to cognitive science and biomimetics. We do way more, oops, this is not the way it should look. We do way more robotics, as you can see here. So things ranging from nonlinear low-level control to automated stability proofs to grasping manipulation, and things even become applied in industry. I want to highlight how amazing things you can do when you use the right kind of learning approach. So we trained single finger controllers, yes, so that we could make them modular by training them to just minimize the slip which a single finger encounters, and we could actually get something where the fingers only communicate through the object. Through the object, not by a central coordination with the master-slave operation possible, which people initially up to now in robotics thought that you would actually need to have central control, would have to compute the force cones on the object. Instead, you can do this directly by computing little local policies for every finger based on just the local tactile sensing. And let me, for the sake of time, this is missing an important part. They're trained on 4 objects, they tested on 80 objects or so. So it's really quite a breakthrough in robotics. We do way more machine learning, and our methods also taken into cognitive science, where you again can, using these reinforcement learning methods, answer really cool questions. Do I still have 1 minute? Okay. So in cognitive science, a lot of people will tell us things which are very weird. On the one hand, you have people like Giga Renzer, Max Planck director in Berlin, who always drives me crazy when he runs around and says humans are not smart because humans do things like that in baseball. When you throw a ball to them, they will not be smart, turn around, run as fast as they can to the point where the ball will be, and then turn around and catch the ball. Instead, what they do is they center the ball in the retina and just do a very simple PD controller called the constant bearing heuristic. And we actually put this complete human situation. We realized this can't generally be true, right? If I throw a ball at somebody in the second row here, there's no way you could use any kind of reactive heuristics. You have to actually plan, because you have 180 milliseconds visual motor delay. If I throw the ball so fast that you can still catch it, this is about 180 milliseconds, but there's no way you can get many updates beyond my initial throw. So you have to really plan. And we again wrote this down as we created a simulation scenario, used our robot reinforcement learning methods, and what we could really show is that if you have a lot of time and a lot of stochasticity in your odometry, then if you have this belief state of trajectory of the ball, you would really look like this catcher did onto the ball and just run to the goal and catch it. But if you have it that your ball is very hard to catch, you actually need to let your estimate diverge a bit, look at the ball initially, then turn around, run forward, and then look again in order to catch it smartly when you know you're in the proximity. And we could show that there is a whole map of control policies which are coined by the reaction time to task duration ratio and the system noise towards observation noise. And we actually figured out that there must be sports which have 3 turns. We could actually figure out that there is in American football a 2-turn scenario, and that 1 turn should even happen in soccer sufficiently frequently, and this 0 turning of the continuous tracking of the outfielder is more or less an island in our policy space. So with other words, makes a lot of sense. With that, sorry, I'm at the conclusion. I hope that you had a little fun about robotics, machine learning for robotics, that have brought our problems closer to you guys, and that you saw the insights we had about reinforcement learning and robotics, which hopefully transferred to deep reinforcement learning. And while you maybe have still some questions, here are some videos on the back from other experiments which use these methods.
Thank you for the wonderful talk. And do you have any suggestions about how to optimize alpha in the constraint?
So at the moment, we are mainly using alpha to explore what kind of actor-critic combinations happen. And for bandits, you can obviously do any combination. For full reinforcement learning, we've only managed to solve 2 cases, right? We've only solved alpha equals 1, alpha equals 2. And the interesting part is that the critic of alpha equals 1 is an unknown one with the log sum x critic, because it's the one which we had from reps, but the critic for alpha equals 2 is the well-known one of actor-critic methods, where you go down this squared Bellman error, or its approximation through the TD error. And while the policy which falls out of it for alpha equals 1 is the softmax policy, while the policy for alpha equals 2 is one which nobody has used up to now, which is a bit slower than the softmax, but much, much safer. So I think it has a lot of future potential. For the actor, we obviously have now we could use now any of the policies from the bandits, but for the critic, you don't get a closed form solution for all the other alphas. So I think there's a lot of room here for people who like math around probability distributions and who like to plug in, I don't know, more complex representations to simply find an alpha where their math can work out. And you actually can very easily instantiate new reinforcement learning algorithms while explaining even why other elements from old reinforcement learning methods worked in this context. Sorry for taking too long.